If you survived the last video, you should have this idea of superposition of states. That's one of the three main points we had in the last video. Superposition of states means that there's more than one state for a particular particle, and the chances of it being in these different states has different probabilities. So, how can we represent the state of a particle? Let's just take position as maybe the easiest one. How can we represent the state? Well, let's start with how we represent the state in macro physics. We've got a space here, and we can look at 3 dimensions of this space and come up with a position. Each vector adds together, and we've got a particular arrow pointing one direction or another, but it defines the position and maybe the direction if we're talking about velocity or acceleration or momentum. Let me get out my drawing board and let's see if we can make a picture help with this idea. Okay, I've got a drawing here of a vector. And we'll start with the simplest one is 2 dimensions, the red being the first dimension, which is the x coordinate, the second dimension being the y coordinate axes, and notice these are added tip to tail, and we come up with this resultant arrow, and that gives us a position in space. If this was a velocity and this was the magnitude or speed of it, then this would be the velocity vector. Maybe it's easier to think of velocity with vectors. Then that covers 2 dimensions. Now, what if we go to 3 dimensions, which of course our world is not flat as a pancake. It is a 3-dimensional world. Here is the third vector, but it's a little hard to show because it's perpendicular to the page, and so it is pointing out. There's the point of the arrow coming out of the page, and the blue would still be the resultant of the x, y, and z vectors. So that goes in and out of the page depending on the quantity that's associated with that z vector. Is that it for dimensions? What about 4 dimensions? Well, what if we put time in here and said that there was a certain time element to this? We couldn't draw 4 dimensions, but we certainly can think about 4 dimensions. Now, what if we have a dimension for each quantum state? And it just happens that there are an infinite number of quantum states, and so there would be an infinite number of orthogonal vectors whose sum total of each quantity of each of those would tell us what the quantum dimension was. And to make things even more fun, some of these vectors are complex, meaning they have a real and an imaginary basis. If we can include all of these in this quantum state, we can actually come up with what's called let me get the brush here going, and let's call it a Hilbert space. And to represent the vector in this Hilbert space, I'm going to use this notation. putting a Greek letter there, can be any letter really, and then I'm showing this representation. So this is going to be the quantum state vector. What do you think of that infinite dimensioned vector? It's a little hard to understand why you'd need something like that. Well, I'm going to take it a step farther and talk about another vector that involves the square root of 1. Square root of 1 happens to show up in the derivations of the wave function. Derivation of the wave function for, remember, the quantum mechanical view of the world is that it's particle and wave duality. So these two things are there. So it turns out that we need a complex number to make things work out right. Complex numbers aren't only used in quantum mechanics, they're also used in classical mechanics. When we talk about electromagnetic waves, the electric wave is perpendicular to the magnetic wave. And so we put 1 as a real number and 1 as an imaginary number. And guess what? When we plot those out, they create a vector. A vector where the real number axis is perpendicular to the imaginary axis. So I'm going to go through some more things on the drawing board and see if I can try and bring this stuff to reality a little bit. All right, here's the vector, and rather than a Greek letter, I've just got the capital A in there. So this is going to stand for a vector of any kind of dimensions that we might need. Not just three-dimensional, not four-dimensional, but it can have an infinite number of dimensions so that we can have an infinite number of probability locations for an object or probabilities of momentums. Now, I'm going to introduce a new idea, which is also a vector. This is C, is a complex number. A complex number has a real part and an imaginary part. Let me put the canvas up there so you can see my pointer a lot better. Here, complex number C has a real part A and an imaginary part, which is the only difference is square root of 1, which you can't evaluate. That makes it imaginary. Square root of 1 times B. And here's a little vector picture of that. Here's the A part in green. Here's the B part in purple. And here's the resultant vector C in red. So what would happen if I multiplied C times a vector, a complex number times a vector? Well, that C would be distributed on all these different vectors, plus if there are no imaginary parts or the imaginary parts are 0 on these vectors, then it will actually add an extra vector. So if I had 100 dimensional space here, infinity is a little hard to think of. Let's think of 100 dimensional space with 100 orthogonal or perpendicular axes to the vector. Then I would take C, and each one of those would turn into a complex vector, so we'd actually have 200 dimensions, 100 real and 100 imaginary. If I take a complex number times a vector A and a complex number 2, a different one, times B, then that gives me another vector R. So I can actually create more infinite dimensional vectors by combining them with operations. And there's more operations than just this right here. Now, another thing I want to introduce is what's called a complex conjugate. This is a way of getting rid of or eliminating the imaginary part. If I have a vector D, which is A plus IB, and a vector E, which is the exact same A and the exact same IB, but this one is subtracted, what happens if we multiply D times E? Well, here's what happens. If you know how to multiply the binomials, you've got the first terms are A squared. The last terms are, because it's a square root of -1. Let's see, I've got a little mistake here. Let me go back and fix that. That should be a plus, because minus IB, where you both the i's are multiplied together, that'd give me a -1, so that'd be a plus b squared. So this would be a plus b squared down here. These center terms, or the inside and the outside terms, cancel each other out. And rather than a difference of squares, which you're expecting, you get the sum of squares because of the fact that this square root of -1 thing is here. Okay, let's start defining another symbology. We had the symbology of this thing, which represented the quantum state vector. Now, let's talk about another thing that's needed when we perform operations with this column vector, and that is a set of linear equations. You can only have linear equations when you're talking about vectors, and that is part of a way of working with linear algebra. Let's consider this. F of x equals m times x. That is the simplest linear equation. That is the typical linear equation. And these coefficients of x are going to be a series of different things. For each one of these quantum state elements, I'm going to say f of x represents a set of linear functions that corresponds to each element of the quantum state vector. The constant m can be, and in italics here, must be a complex number. Remember, I said the math requires that this be complex. So in addition to each real vector, we have an imaginary vector. If we take this new symbol, which look is the mirror image of this symbol, which represents the column vector, then we combine the two symbols. And when these two symbols are combined, these linear functions are actually being multiplied by, let's see, that should be f of x. They're missing a little parentheses there. But anyway, I won't take the time to keep going here. I won't take the time to interrupt. This becomes a bracket, bracket. And so that it's kind of balanced, we use 3 letters for each side. I say this column vector of the quantum state is a ket vector, and the corresponding set of linear functions that goes along with it is a bra function. Now, I like to call it a bra because it's bracket. If you use bra, then you're starting to introduce something else that you're thinking of, not an article of clothing. So this is a bra vector and a ket vector. Now, consider if f of x is equal to x. That's really simple, where m is 1 or m is Let's see. M is the forces this to be a complex conjugate. Now, what's a complex conjugate? Well, for each vector in here, we have if this is of the form A plus IB, where A is real and B is imaginary, then we would have a corresponding linear equation that uses the coefficient of A minus IB. So when we multiply them together, as we did on the last screen, we come up with the x squared, which is a real number. And I put these things around it because it's going to be positive. Can have a negative physical quantity, but you can't have a positive quantity. And this real number then can, if we're talking about position, the quantum state of position, this represents position probability, which is really important because now we can come up with something that's kind of makes sense. Have you lost yourself in all these weeds? Has your brain started to wander and you say, where did we come up with all these things? Remember, this all started with the idea of superposition, in that x can has a probability of occupying one of an infinite number of states. An infinite number of states. So there's going to be a corresponding infinite number of linear functions that goes along with this. Now, that doesn't mean we have to write down all these different values, because we can generalize this situation and come up with the result. Now, did we meet the goal of this video? The goal is to understand superposition of states in terms of a vector, a ket vector, and a bra vector that goes along with it. Those two together can, provided there's a complex conjugate involved, those will put everything into real numbers, and then we can come up with the values of a measurement. So, where do we go next? What is the goal? Where are we going next? We want to figure out the laws of motion according to these little tiny things in the quantum mechanical world, and compare them to the laws of motion of Newton or macro physics. Remember, I say macro and micro. Macro works when things are large and at least in the dimensions that we experience every day, and micro is involved in dimensions that we can't experience every day. We have to use special measuring devices to see that. So let's see if we can get there, hopefully in an easy, clear, and understandable way. If I lose you, comment. Let me know what's wrong and we'll try to fix it.